So I wanted to expand a little bit more on what the first couple of videos in 4M talked about. And so here's a table of values. Again, I apologize for the watermark there. Not much I can do. That just kind of summarizes what each of the values in a function mean, depending on whether they're positive or negative, and whether we're talking about the function or its first derivative. And so hopefully at this point, you've worked through some of the problems and you figured out that when you have a function, when a function is positive, your value is above the x-axis. So for example, if I give you x and y axis here, just a quick sketch, and my function is doing something like that. And so I ask you, where is the original function positive? Well, the original function is positive on this interval here and this interval here because it's above the axis. Likewise, if it's negative, it's below, which would be here and here. And the x-intercepts, which is what you spent a lot of time in Algebra 2 on, was finding this. I guess I could color that a different. This guy, and this guy. Then in 4M, you explored a little bit of what the first derivative does. And the first derivative, which again gives you the slope of the line tangent to a function at a given point. It's also the instantaneous rate of change. And so you guys found out that if the first derivative was positive, that your function was increasing. And so that occurred, I know we're going to get a lot of colors here, but that occurred from here up to this top point. And it also occurred from this bottom point up here, which remember we called the bottom point a min and the top point a max. And then the first derivative equal to zero, sorry, negative, it's decreasing. And then equal to zero, we said that it's a stationary point, which we also called critical points, maxes and mins, and all that stuff. And so, but there was this third option that I mentioned in the previous video, where when you take the first derivative and you set that first derivative equal to zero and solve, you get possible locations of a max, a min, or this other third option. And so we're going to talk a little bit about what that third option is. And so before we do that, I want to talk a little bit about the second derivative, which again, the second derivative is just the first derivative of the first derivative, using all the same rules we've been using, is what's another way we can use the second derivative? And so when you're finding maximum and minimum values, you can do your first derivative, set it equal to zero, but we're also looking at some different ways, the behavior of the graph that occurs other than it just being a minimum or a maximum. And so we determined that a minimum value shifts from decreasing to increasing. So it goes down as we move left to right, it goes down, flattens out, and then goes back up. And then a maximum value does the opposite. It increases, so it goes up, flattens out, and then it goes back down, and we call that a maximum value. And so what happens though if you find these values? So we found these values at C by setting the first derivative equal to zero. And so the question is, what happens if a function decreases, flattens out, and doesn't increase? And so two possible situations that we need to explore a little bit are, what happens if you find these critical values, these stationary points, and you do your number line and you test the values, but all of a sudden you have a function that decreases, flattens out, and then continues to decrease, or increases, flattens out, and then continues to increase. And these seem like these are rare functions. So like, when is that ever going to happen? A very common example of that is the function y equals x to the third. And so with y equals x to the third, your function increases, passes through the origin, but then it doesn't go back down like a quadratic. It actually goes back up. So what's interesting about the function y equals x to the third is this function increases on its entire domain, all real numbers, except at x equals 0. At x equals 0, it flattened out. So this particular value at 0, 0, it's not a minimum, it's not a maximum, so what is it? Well, we need something new. We need some other type of analysis to tell us what exactly is going on at this value x equals 0, or any other value on a function where you have decrease, flatten, decrease, or increase, flatten out, increase. And so we actually call these horizontal points of inflection. Now, just so you're not confused that IB is international, so you will get some unique spellings. And from now and then, you'll see inflection with an X. We will not do that. I believe that is the British spelling of inflection, but just know that you will see some interesting spellings now and then. And so what is a horizontal point of inflection? Well, I'm using the function we discussed earlier, y equals x to the third, as an example. And so what happens is you find the first derivative and you set it equal to 0. And when you do your analysis, you create your number line, you test the values, it does not change from increasing to decreasing or decreasing to increasing. And so what happens is it flattens out, and we still do have a horizontal tangent at that point, but it continues doing whatever it was doing before. So if it was increasing and flattens out, it continues to increase. And so we call these horizontal points of inflection. And so let's summarize what these stationary points are actually called and what they are. And so again, stationary points, I will try to use the different synonyms for these so you get used to all the different ways you'll hear it. So stationary points, critical values, all mean the same thing. And so here's the formal definition for a stationary point. So it says at some point x equals c, which should be anywhere on the function, where the gradient, we haven't used that word in a while, so the gradient is just the slope of the tangent, is equal to 0. And so you guys did this. If you've already done the 4M homework, you did this, where you found the first derivative and set it equal to 0. And so we say that if the gradient is equal to 0, then we call those either a maximum, a minimum, or a horizontal point of inflection. And these points of inflection are going to come into play a little more as we kind of dig deeper into these graphs and how we analyze them. So first example of this is find any maximum, minimums, or points of inflection of the curve y equals x to the third plus 2. Now, if you remember your function transformations from earlier in the year, we know that this is just y equals x to the third, which looks a little something like this. But then what does the plus do? It essentially shifts this up 2 points. But let's look at this from more of a derivative analysis perspective. And so we find the first derivative. So dy dx in this case is equal to 3x squared. And then that's it because 2 is a constant. And so the next step is we take that first derivative and we set it equal to 0 with the hopes of finding any maximums or minimums. And now we have this third option. And so when you solve, if you divide by 3 and you square root, we find out that there is only one possible value where this can occur, and that's at x equals 0. And again, that's pretty obvious because we already talked about it. And then from there, you create your number line, and you place the 0 on it. And then we test values on either side. So I'm just going to pick -1 and +1. And be careful here. Make sure you're testing these values in the first derivative. We're not plugging them into the original function because we want to know what is the slope of the tangent at these given points. And if you've already watched the 4M video, you know that I don't really care about the number. I just care about whether it's positive or negative. And so plugging -1 into this, -1 squared is +1 times 3 is a positive. And so that tells me this function is increasing, which matches up with what we already know about the graph. It then flattens out at x equals 0, but then when I plug in +1, it basically gives me the same value. 1 squared is 1, times 3 is 3, so it's positive. So it continues to increase, which again matches up with our graph. So what does that tell me about the value at 0? Well, number one, I know it's 0, 2, just by plugging that into the function. But I now know it's not a maximum, because if it was a maximum value, it would go from increasing to decreasing, which it is not. It's not a minimum, because minimums would need to decrease followed by increase. So it doesn't do that either. So in this particular example, at x equals 0, 0, 2, we actually have a point of inflection. And so I want to kind of expand on what that actually means to be a point of inflection. And this is really the core idea behind the second derivative. So what the second derivative actually finds for you is something called concavity. And we briefly discussed this in class before we left last week. And that was, what does it actually mean to be concave up or concave down? I want you to think of concave up as just what what is the behavior of a parabola that opens up? Or what is the behavior of a parabola that opens down? So even though we lose, in a lot of these functions, we lose some of the symmetry, you can think of these types of functions, polynomial and other ones, as not being one nice smooth curve, but being made up of sections that act like parabolas that open up or parabolas that open down. And so if I look at this graph of x to the third, and I know it's x to the third, or could be x to the third because of the n behavior, is I see it going down as you continue to the left, and I see it going up as your values increase. But bigger picture, I actually see that this is acting like a parabola that opens down up until right about there. And so this function from negative infinity up to x equals 0 seems like it's acting like a parabola that opens down, and so it appears like it's concave down. And then as it transitions over to this side, it looks like it shifts into a graph that acts like a parabola that opens up. And so we say that this particular part is concave up. So going back to my graph here, we said that this was a horizontal point of inflection. Well, the reason we call it a point of inflection is because that point of inflection is kind of the fence or the separator between parts of your graph that are concave up and concave down. So if we look at this particular graph, it appears like the stuff to the left of the y-axis here is acting like a parabola that opens down. And so we've said that that is going to be concave down, and then this part to the right of the y-axis appears like it's concave up. And so what separates these two parts, where one part is concave down and one part is concave up, that's what we call these points of inflection. And so a point of inflection is a place where the concavity of a graph changes between concave up and concave down. So if it shifts from concave down to concave up, we call that a point of inflection. Now, we are going to run into issues later where what happens if it's concave up, stops, but then continues to be concave up. We'll have to explore what that actually means, and we'll find out that those are not points of inflection. So a point of inflection only occurs when the concavity of a graph changes from concave up to concave down. So adding to our table, you will definitely want to write this down. This would be a good place to pause, is we have our notation. And so we've got the function, which when it's positive, it's above the x-axis. When it's negative, it's below the x-axis. And when it's 0, it's an x-intercept. And so we then had the second part of this, which was the first derivative. When the first derivative is positive, we know it's increasing. When it's negative, it's decreasing. And when it's equal to 0, it's a stationary point, which we determined was either a maximum, a minimum, or my little shortcut here for point of inflection. And so what the second derivative tells you is it actually tells you whether a graph is concave up or concave down. And so if a second derivative is positive, we know that it's concave up. If the second derivative is negative, it's concave down. And if the second derivative is equal to 0, we know it is a possible point of inflection, knowing that a point of inflection only occurs when it transitions from concave up to concave down, or concave down to concave up. And so our steps, again, I will let you guys pause if you need to for this. The second derivative test is essentially the same idea as the first derivative test. The only difference is we're going to be doing the number line with the second derivative, not the first derivative. So your steps are going to be, you're going to find the first and second derivatives. You're going to take the second derivative and set it equal to 0 to find these possible points of inflection. Again, possible because we know it could not be a point of inflection if it doesn't change concavity. And so then we use a number line similar to what we did before with first derivative and maximum and mins. And then using that information, we determine, is it actually a point of inflection? And again, this number 5 is very important. A point of inflection only occurs when it changes concavity. So if there's no change in concavity, we don't call that a point of inflection. And then step 6, which is optional for many of these problems, sometimes they ask you to find the x and y coordinates. Most of the time, I'm just going to ask you to find the x value. And so let's look at an example here and find out what it actually looks like. And I've got the homework listed there, so we'll kick that to another slide. So example 2, determine the coordinates of any max, mins, or points of inflection, and then sketch it. And so we take our function here, which is an x to the fourth. Step 1 is we find the first derivative. So the first derivative in this case, the 3 is gone because the derivative of a constant is 0. Hopefully you're getting quicker on those. And then we get 12x to the second minus 4x to the third. And so now before we jump into concavity and all that, we are asking about maximums and minimums. So what we're going to do right now is we're going to go ahead and set this particular function, 12x squared minus 4x to the third equal to 0. And we're going to solve, looking for any possible maxes and mins. And so solving this, we would definitely need to pull out common factors. And so our greatest common factor is 4x squared, which leaves us with 4x squared times the quantity 3 minus x. And solving, we get x equals 0 and positive 3. And so then we do our number line, similar to what you did in 4m. And we place 0 and 3. And then we're going to choose values that are on each of the 3 intervals. The 3 intervals being x is less than 0, x is between 0 and 3, and x is greater than 3. So again, pick the easiest values you can. I'm going to go with -1, 1, and 4. And I'm going to plug these values into the factored form of my first derivative. And I don't care about sign or the numbers. I only care about the actual signs. And so if I plug in -1, -1 squared is positive 1 times 4. So I know it's positive on the outer part. And then -1 in here, 3 minus -1 gives me a positive. So I know that's positive. So since this is first derivative, that tells me that my function is increasing when x is less than 0. I then repeat that same process for +1 out front. Basically, any number you plug in out here is going to be positive because you're squaring it. And then 3 minus 1 is still going to be positive. So it looks like this is still positive, which means my function is still increasing. And then if I plug in 4, I get a positive out front, but then 3 minus 4 creates a negative inside, which is negative. Therefore, my function decreases. And so what does that tell me is happening at x equals 0 and x equals 3? Well, at x equals 0, it looks like it's increasing, flattening out, but then continuing to increase. So what does that tell me about this particular value? That's going to be one of those points of inflection. And then at x equals 3, it's increasing followed by decreasing. So I know this is going to be a minimum. Now, before we sketch, we want to do a little bit more. Again, feel free to pause the video if you need to take a look at that. We need to do a little more because I want to know also about any points of inflection. And so I'm going to do the second derivative. Now, what's interesting here is the second derivative, when you find it and you set it equal to 0, will find points of inflection. Now, the interesting thing about the first derivative, when you find stationary points, will give you maxes, mins, and horizontal points of inflections. So these specific points of inflections are very unique because they show up on the first derivative, but they're still points of inflection. So they should also show up when we do the second derivative. So again, those horizontal points of inflection where you increase, flatten out, and then increase again, those specific values should show up in your first derivative, but they should also show up in your second derivative. So right now, it appears like we've got one of those here at x equals 0. So hopefully this value of x equals 0 also shows up in the second derivative. So let's see what happens. So if this is my first derivative, 12x squared minus 4x to the third, and I find the second derivative, so the second derivative would be 24x minus 12x squared. And now I repeat the same process as I did for the first derivative. I set it equal to 0. So 24x minus 12x squared is equal to 0. Same idea, you want to pull out a common factor, which in this case is 12x. That leaves me with 2 minus x is equal to 0. And then when I solve, I get 2 possible points of inflection at 0 and 2. So there's that 0. We already knew that was a point of inflection, so that's a really good sign that it showed up on the second derivative. But now we've also got this other guy at 2 who could be a possible point of inflection. And so we do another number line. This time we're placing 0 and 2. And I'm going to choose values again on the 3 different intervals. So I'll pick -1, +1, and 3. Now there's a lot going on here, so you have to keep track of what goes where. -1, 1, and 3, I'm not going to plug them into the original function because that would give me the y coordinates. And I'm not going to plug them into the first derivative because that would give me the slope of the tangents. I don't want that. I want concavity. And so I'm going to have to plug those into the second derivative. And just like we did before, I don't care about the numbers, I only care about the signs. And so if I plug -1 into the 12x times the quantity 2 minus x, I get a negative out front, and then 2 minus -1 is positive. So that tells me this is negative, and that tells me that in this particular region, my graph is concave down. Then I plug in +1, gives me a positive out front and a positive on the inside, which is positive, which tells me my graph is concave up in this region. And if I plug in 3 out front, it gives me a positive. And trying to avoid the watermark if all possible. So it gives me positive, and then 2 minus 3 is negative. And so that tells me it's negative, which tells me in this region, it's concave down. So putting all of this together, here's my function. So I know that at x equals 0, I have a horizontal point of inflection. And let's even go back further. This is an x to the 4th polynomial, so it's an even power, and it has a negative leading coefficient. So I know the end behavior, it's going to be down and down. We just got a whole lot of junk that's going on up in between those two. So my function is doing something like this. It's increasing up until 0. And if I want to know what the actual coordinate is, I can also plug 0 into the original function. And I know we're getting a little cluttered here, but 0 knocks these out, and so it's 3. So I know this function is at 0, 3. So it looks like my function is increasing. That is awful. Increasing up until the point 0, 3. Then we get a horizontal point of inflection, which means it flattens out, but it's not a maximum or a minimum. What it does is it then continues to increase. And it increases until the value x equals 3. Now what I'm going to do is I'm going to ignore the concavity for just a second. And at 3, I know I have, oh, and I wrote minimum here. My bad, guys. Let's go all the way back. So hopefully you fixed that when we did it. That should be maximum. Wasn't paying attention. So that is a maximum value. And so at 3, you have a maximum, and then once it hits 3, it decreases. So it does a little something like that. So now let's see how this particular value right there is a horizontal point of inflection. This is a maximum. And let's see how our second derivative plays into this now. So we said that at 0, our concavity changed from a negative to a positive. And that looks like what happened here. Notice the graph is concave down because it appears to look like the left side of a parabola that opens down. And then it shifted to concave up. But then at x equals 2, it also looks like there's a point of inflection. So the graph shifted from concave up to concave down, which appears to be what's happening here. So it seems like at this point, my graph, and let's do this as a different color, it seems like it's acting like a parabola that's opening up, so concave up, but then all of a sudden it shifts and turns into a graph that looks like it's acting like concave down. So at this particular value here, we have a point of inflection. So a lot of stuff going on in that video. I had a couple other slides, but I'll keep that for a separate video. So the key components here is when you find the function is recognizing when a function's positive, negative, and 0, what that actually means. And the first derivative being positive is increasing. When it's negative, it's decreasing. When it's 0, you have a stationary point. So it's either a maximum or minimum or a horizontal point of inflection. And then the second derivative kind of describes the behavior of a graph. So if a second derivative is positive, the graph is concave up, and it has this behavior. And if it's negative, it's concave down. And if it's 0, we have a possible shift between concave up and concave down. So hopefully this was helpful.